Fatigue and recovery in exercise. Fatigue is the reduction in force production or power in exercise or being unable to continue. For example, someone playing netball may need to take a time out in the game because they fatigue too much and can't carry on. There are various ways in which fatigue can occur, and some of these ways are depletion of fuels needed for energy systems to work, such as glycogen and phosphocreatine. A build-up of waste products such as hydrogen ions and lactic acid also can cause fatigue. Another reason why fatigue can occur is because of a decrease in neuromuscular system's ability to continue contracting muscles. In different activities, fatigue is induced in different ways, and this can be down to what type of exercise it is. Exercise can be determined by its intensity, duration, and fibres used. For example, a shot put would mainly use fast glycolytic fibres and have a very high intensity but low duration. An 800-metre sprint would mainly use fast oxidative glycolytic fibres and would have both moderate intensity and duration. However, a marathon uses slow oxidative muscle fibres and has a low intensity but high duration. Changes in the criteria used to measure exercise can lead to fatigue being induced in different ways and at different times in performance, and this has an effect on the recovery of exercises. There are 3 different types of fatigue, which are local, general, and chronic. Local fatigue is from repeated contractions of the muscles without rest, and normally occurs in sports where there is a high demand for muscle contraction. General fatigue is from post-training or game, and is feeling of being physically or psychologically weak. For example, after a netball match, a player may feel drained of energy, and this is because of general fatigue. The last type of fatigue is chronic fatigue, which is a weakened immune system from excess training or having an inadequate recovery. There is also psychological fatigue, which is where physically you are able to carry on, however you can't psychologically. This can be due to a lack of motivation, so you don't reach your full physical ability. An example of maximal intensity, short duration activity is a 100-metre sprint. The muscle fibre used here is fast glycolytic because they can produce short bursts of power needed in the event. However, they only last for a short period of time, so fatigue will occur early in the event. The dominant systems in this activity are the ATP system and the phosphocreatine system. For the first 3 seconds, solely ATP is used, and when this has all been broken down, the phosphocreatine system resynthesizes the ATP by splitting the bond between phosphorylase and creatine, so ATP can continue to break down to release energy. There are no harmful waste products produced using these systems, however a waste product is phosphorylase and creatine before they are resynthesized back together by the aerobic system. The main reason why fatigue happens in these systems is because when phosphocreatine breaks down to resynthesize ATP, it can't be used again until it is resynthesized by the aerobic system. This leads to fatigue because the PC system can no longer resynthesize the ATP, so the muscles don't get energy to contract. This is shown in this graph where it shows how after time the PC levels drop in exercise. When you fatigue, it causes your performance level to drop. For example, in a sprint towards the end you won't be able to run as fast because you would start to fatigue. There are ways in which fatigue can be reduced in order to maintain a higher performance for longer. For example, in high-intensity short-duration activities you can take phosphocreatine supplements can be taken such as creatine. This increases the level of phosphocreatine in the body, so there is more PC to resynthesize ATP. Therefore, a high level of work can be achieved for a longer time before fatigue kicks in. This type of exercise has a relatively small recovery time compared to longer duration exercise, as all that needs to happen is ATP and PC need to be resynthesized. For this to happen, 3 to 4 litres of oxygen is needed. For 50% of PC to be resynthesized, it takes 30 seconds. For 75% of phosphocreatine to be resynthesized, it takes 1 minute. And for all of the phosphocreatine to be resynthesized, it can take up to 3 minutes. This graph shows the level of VO2 during exercise and recovery. The oxygen deficit is the shortage of oxygen during exercise where the VO2 isn't sufficient enough to meet the activity's demands. As you can see from the graph, in this type of activity there is a large oxygen deficit because it is working anaerobically, so oxygen isn't being used. This means that in recovery, more oxygen needs to be taken in to compensate for the lack of oxygen in the exercise. This process of recovering by consuming more oxygen is called EPOC, excess post-exercise oxygen consumption. This occurs after you stop exercising. At first there is a rapid decrease in VO2 before it becomes more gradual. During EPOC you breathe faster and deeper to increase the amount of oxygen in your body and to return the body to its pre-exercise state. In high intensity exercise there is a larger EPOC because you've been working anaerobically in the absence of oxygen, meaning that more oxygen is needed in the recovery stage to return the body back to normal. There are two components to recovery, which are the faster lactic component and the slow lactic acid component. It is the lactic component which is used for high intensity exercises like the 100-meter sprint, because it is this part that is responsible for resynthesizing ATP and PC, and the resaturation of myoglobin and hemoglobin with oxygen. By maintaining an elevated VO2, it allows more oxygen into the body, which is used to resynthesize the phosphate and creatine back into phosphocreatine, and then allowing ATP to also be resynthesized, so the body is recovered. Moderate intensity and moderate duration events are activities such as a 400-meter sprint. The muscle fibres used here are fast oxidative glycolytic fibres because they are in between fast glycolytic and slow oxidative fibres, so are best for moderate intensity and duration events. The main energy system used here is the lactic acid system. This becomes dominant after 10 seconds when the PC stores are depleted and would last for the remainder of a moderate intensity and duration event. The main fuel used by the lactic acid system is glycogen, which is broken down by enzymes into glucose and further into pyruvic acid, before being converted into lactic acid in the absence of oxygen. One way that fatigue can happen in the lactic acid system is due to a depletion of glucose. If there is not enough glucose or it runs out, then there is no fuel for the lactic acid system to happen. Therefore, it won't be able to resynthesize any ATP, which causes fatigue. The lactic acid system produces a harmful waste product of lactic acid. This is composed of lactate and hydrogen ions, and the hydrogen ions are harmful because they increase the acidity in the body, which is called acidosis. This denatures the enzymes, which causes the process of breaking down glycogen. This then means that the process of anaerobic glycolysis can't happen, so ATP can no longer be resynthesized by the lactic acid system, which can cause fatigue. This graph shows the lactic threshold. Obla is the onset of blood lactate accumulation and occurs when the waste product of lactic acid starts to build up too fast for the aerobic system to remove it, so the levels of lactic acid in the blood start to dramatically rise. After Obla is where you start to fatigue because the pH inhibits the enzymes causing glycolysis to stop working, so ATP can't be resynthesized. As you can see, after Obla there is a rapid increase in the amount of lactic acid found in the blood. At 4 millimoles of lactate is the lactate threshold, and this is where fatigue starts to happen because of the drop in pH levels. When this fatigue happens, it causes performance levels to drop because if ATP can't be resynthesized, then energy can't be released for the muscles to contract. A way to avoid fatigue happening or to delay fatigue would be to take glucose ingestions. These supplements contain glucose, causing the amount of glucose stores in the body to increase. If there is more glucose in the body, it causes there to be more fuel to be used in glycolysis, so a large amount of ATP can be resynthesized. Recovery from this type of exercise requires the lactic acid that has accumulated to be removed, and this can take up to 20 minutes. Another thing that needs to happen is the glycogen stores need to be replenished, which in this type of exercise can take up to 2 to 3 hours. ATP and PC also need to be resynthesized because they were used in the first 10 seconds before the lactic acid system became dominant. This activity has a large oxygen deficit size because it works anaerobically without oxygen. This means that there is a large oxygen depth, so there is also a large EPOC recovery time, to increase the amount of oxygen in the body until it has returned to a resting level. In recovery, both fast and slow components are needed for moderate intensity and duration exercise. In the fast component, ATP and PC are resynthesized by using the aerobic system to create energy to resynthesize ADP and a phosphate back into ATP, and the waste products, phosphate and creatine, back into phosphocreatine. Also in this stage of recovery, myoglobin and hemoglobin become saturated again. By maintaining an elevated breathing rate, it allows oxygen to resaturate the hemoglobin in the blood, which can then transport the oxygen to the muscles and resaturate the myohemoglobin. This process of replenishing oxygen to the myoglobin and hemoglobin can take up to 1 to 2 days. During the lactic acid stage of recovery, the glycogen used in anaerobic glycolysis is replenished. After high-intensity exercise, this can take up to 2 hours before it can be sped up by a high-carbohydrate diet, because the carbohydrate can be used to convert into glycogen. The best times to eat carbohydrates to increase glycogen stores is during the 2 hours after exercise, because this is when muscle cells are most receptive to carbohydrates. Another thing that happens in this stage is the removal of lactic acid. There are a few ways in which lactic acid can be removed. One way is by converting it back into pyruvic acid. This is done by oxygen breaking the lactic acid down so it becomes pyruvic acid again, so it can be ready to enter the aerobic Krebs cycle and to be further broken down into carbon dioxide and water, which are easily removed. Another way lactic acid can be removed from the body is by converting it into glucose. This is done through the Cori cycle, which is where lactate is carried in the blood to the liver, where it can then be converted into pyruvate acid before being converted to glucose, which can be stored in the liver or muscle tissue as glycogen, and then later be used as a fuel source for the lactic acid system. A way to speed up this recovery is by soda loading. This involves drinking sodium bicarbonate a few minutes before an event, which neutralizes the lactic acid that accumulates in the blood. It does this by increasing the amount of hydrogen carbonate ions in the blood, which absorb the hydrogen ions from lactic acid forming carbonic acid before breaking it down into carbon dioxide and water. Sodium bicarbonate can also be used to reduce fatigue as it delays the lactic acid buildup so you can work anaerobically for a longer period of time. Low duration, high intensity exercise is activities such as a marathon. The fibre used here are slow oxidative fibres because they allow exercise for a long period of time without fatigue, however can only be used at a low intensity. The most dominant energy system in this event is the aerobic system. However, because of the complex process, it takes a while for the system to become dominant, so the phosphocreatine and lactic acid system are used up first before the aerobic system becomes dominant. The main source used here is glycogen, which can be broken down into glucose and pyruvic acid before entering the Krebs cycle and then the electron transport chain to resynthesize 38 ATP. Protein can also be used as a fuel for the aerobic system. It can be broken down into amino acids, which enter the system as either pyruvic acid or acetyl-CoA, which is the stage after pyruvate acid. The last fuel that can be used in the aerobic system are fats such as glycerol or fatty acids. Glycerol enters the system as pyruvic acid, and fatty acids can enter the system as acetyl-CoA. The most common cause of fatigue in low-intensity, high-duration exercise is the depletion of glycogen stores. Like the lactic acid system, this is the main source of fuel, so that if there isn't enough or it runs out, then the aerobic system can't continue to work and ATP won't be able to be resynthesized. This causes fatigue because if ATP can't be broken down to release energy, then the muscles won't get the energy they need to contract. Some waste products of this type of exercise are water and carbon dioxide, which mostly aren't harmful because they are easily removed by exhalation from the lungs. This means that they don't contribute towards fatigue. The carbon dioxide formed at the muscles can be removed in 3 ways, which are in the plasma, which is 3%, 27% is removed from the body as carbaminohemoglobin, which is where it is carried in the hemoglobin, and 70% is removed as carbonic acid. Carbonic acid is formed from bicarbonate and hydrogen ions, which can increase the acidity of the body and induce some fatigue. These ways transport carbon dioxide to the lungs where it can then be exhaled. Heat is another waste product, however, it isn't harmful because it is easily removed through evaporation. Water can also be removed through the body by sweating from the skin or exhalation. Some causes of fatigue in this system are neuromuscular factors. Over long duration exercise, potassium is lost, which can cause disruption to impulses. Potassium is found on the inside of motor neurons, and when an impulse travels down the neuron, a wave of depolarization happens, so potassium ends up on the outside of the neuron. For another impulse to travel down the neuron, the ions need to reset to where they were before the impulse travelled along. However, in prolonged exercise, some of the potassium ions can get lost after the wave of depolarization happens, so they can't reset. This means that the impulses can no longer travel down the neuron. This causes fatigue because although some impulses are being sent from the brain, they aren't reaching the muscles to tell them to contract. Another way fatigue can happen is through a loss of acetylcholine. This can occur through a lack of cholinesterase, which is an enzyme needed to clear acetylcholine from the neuromuscular junction by breaking it down and preparing it to be used again. If acetylcholine isn't cleared and replaced in the neuromuscular junction, or not enough is, then the impulse can't cross from the neuron into the muscle. This means that the muscle won't contract, and it also results in fatigue. The last neuromuscular factor which can cause fatigue is loss in calcium. Calcium is needed for muscles to contract because it binds with troponin, allowing myosin heads to bind with actin to form a cross bridge, and therefore shortening the sarcomere to make the muscle contract. However, the calcium pumps up the sarcoplasmic reticulum can leak, causing a decrease in the calcium released into the muscles. This then reduces or weakens the muscle's contraction. Fatigue can be delayed by carbo loading, which increases the glycogen stores in the body. It works by around 6 days before an event, minimal amount of carbs are eaten, carbs such as bread and pasta, which leads the body to think that there is a problem, so it becomes more sensitive to carbohydrates and stores more glycogen than normal. Then, a few days before an event, lots of carbohydrates need to be eaten, so more will be stored normally, so there would be a higher store of glycogen in the body. This then allows more exercise before fatigue happens because there is a higher store of your glycogen in the body, allowing the aerobic system to resynthesize more ATP for longer periods of time. Recovery from long endurance events takes a much longer time than from shorter events. It can take up to days to fully recover. The replenishing of glycogen can take up to 3 days in long duration activities because a large store of glycogen has been used, so more needs to be replenished. Metabolic demand is the heart's need for oxygen during and after exercise because it is a muscle. After exercise, the heart needs more oxygen than normal to maintain an elevated heart rate and stroke volume, resulting in an elevated cardiac output. In the recovery stage, there is an elevated oxygen input, so the heart can get this oxygen that it needs. Low intensity, high duration activities also have a small oxygen deficit because they are working anaerobically, so the provision of oxygen meets the demands. However, there is still an oxygen deficit because it takes a while for the aerobic system to start working, so at first you are still working anaerobically. This also means that the EPOC time is smaller because there is less of an oxygen debt, so less oxygen needs to be inhaled to recover. The aerobic system uses both fast and slow components of the EPOC to recover, to resynthesize ATP and PC stores, resaturate hemoglobin and myohemoglobin, remove lactic acid, and to replenish glycogen stores. The faster lactic stage lasts for around 2 to 3 minutes and uses around 3 to 4 litres of oxygen. The faster it resynthesizes the ATP and PC stores that were used at the beginning of the activity by supplying the phosphocreatine with oxygen, so it has the energy to resynthesize. It also resaturates the hemoglobin and myohemoglobin with oxygen by maintaining an elevated breathing rate so excess oxygen is taken in. The lactic acid stage takes a lot longer and uses more oxygen. It is responsible for removing the lactic acid that has accumulated in the body during this exercise by sending oxygen to the muscles where lactic acid is. To aid recovery, it is useful to have a light cool down after exercise rather than complete rest. This helps the skeletal muscle pump, which is a mechanism to help blood return to the heart, continue to work because it needs muscles to be contracting, and a cool down maintains muscle contraction. It's important to do this to recover because it allows blood to continue to return to the heart, where it can be pumped to the lungs to be oxygenated, and then pumped around the body so the muscle can continue to receive oxygen. If you rest straight away, then blood will start to pool and the muscles won't be receiving the oxygen that they need to recover. Another strategy is to take an ice bath or wear a cooling vest after exercise because it reduces the body's temperature. This speeds up recovery because it helps to remove waste products from the body by increasing the body's ability to transport the waste products around. The ice vest can also be worn before exercise to reduce recovery time because they decrease the body's temperature to stop it from increasing too much during exercise.